Hi everyone, I'm Professor Bergasser, and in this video we're going to be looking at torque, leverage, and balance. Now recall that torque is the rotational equivalent for force. It's the thing that causes objects to start rotating or change their rotation rates. And we're going to see how how torque balance allows us to get a handle on leverage, and these are the the mechanical advantage gained by levers, which are one of our three simple machines, along with pulleys and inclined planes, and how torque balance actually gives rise to physical balance, and particularly the balance of a person walking or standing or dancing. So as a reminder, if we want to quantify our rotational motion, we need to use our rotational quantities, and these quantities are very similar to our translational quantities. We have angular displacement that describes how much rotation has occurred for an object in angles, in this case usually radians. You have the angular rotation rate, which is that change in orientation divided by the time it takes for the orientation to occur. That's the angular rate. And then we can also look at how the angular rate changes with time, and that's of course an angular acceleration. And you can have higher order term changes as well. But these three terms are going to define most of the rotation that we're seeing in this class. And keep in mind that I've written these as scalar quantities, but you should also consider writing these in vector quantities because those directions of displacement, angular rate, and angular acceleration all depend on the rotation axis and whether you're moving clockwise or counterclockwise around that axis. Now these quantities give us a way of measuring how much motion, rotational motion, has occurred, but they don't tell us much about how that motion actually took place. And we've had the similar discussion when we talked about translation. How do we get an object to actually accelerate? If you recall, that required a force, an interaction to occur. So we're going to have the same case of an angular force, but it's going to be a slightly different mode because we're talking about slightly different types of motion. So I have my bicycle wheel here, and we can use this as an experimental tool to see what kind of things cause this bicycle wheel to start spinning around. Well, so the most natural thing to do is just to grab the wheel and pull it in that direction, and that causes the wheel to start spinning. But notice what I did in that case. I grabbed the wheel here and I applied a force that is tangential to the circle of the wheel. If I grab the wheel and I try to push down or pull up, nothing happens. So clearly there must be a tangential force to cause this wheel to start spinning. The other thing notice is that if I pull closer to the rotation axis here with the same force, I end up getting a lot less rotation than if I pull up here with the same amount of force. It's easier to pull the wheel around at this larger radius than it is to pull it down here to get it going into a circle. And the other thing, of course, is if I apply a force toward me, I get one type of rotation. If I apply a force the other way, I get the opposite rotation. So something about the direction of force must tell us something about the rotation direction as well. So using those observations, we can come up with three general rules of how rotational acceleration occurs and how that rotational acceleration is maximized. It's maximized when the force that I apply is, of course, large. If I pull harder, I'm going to get more rotation. It has to be a force that's applied tangentially to the rotating surface, in this case, the wheel itself. And you get more rotation when you apply a force that's offset a greater distance from the center of mass, or the center of the rotation axis. Something about that distance is something that helps us spin an object further along. So we can combine all these observations and define a new quantity that we call torque, which is the rotational force that encompasses these patterns that we observe. And in fact, they're encompassed by simply using the cross product as a way of combining our positional and velocity force vectors. So to see how this works, we have our term here, which is a torque, which is a vector quantity. That is our rotational force term. And that depends on two quantities that are cross product together. One is the displacement from the origin, or in this case the rotational axis, to where I apply the force. And that's cross product into the actual force that's applied to our, in this case, our wheel. And of course, a cross product is dependent on the length of the vectors of the quantities that we're looking at times the sine of the angle between them. So that's what that angle is there, is the angle between the force and position vectors. And the resulting quantity has a direction that is perpendicular to both of those vectors. And that direction is determined by the right-hand rule, as with other cross products. So let's go back to our wheel and look schematically at how this comes about based on the experiments I did. So remember, if I applied a force, that is in this direction, right, I'm applying it a distance r. I'm applying it a distance r from the center of rotation here. So the torque that I'm calculating is really r cross f, and that is something that points into the screen or into the board. So we have our into the board unit vector to indicate that distance. And in this case, these vectors are perpendicular to each other, so the sine of the angle is sine of 90 degrees, and that's just 1. So that's why I've included a sine there. And as we apply that force again, if I apply that force there, what we notice is that it starts to rotate up in this direction. It accelerates, angular acceleration is increasing the rotation rate in this direction. And if we go back to our right-hand rule again, that rotation axis is going to point into the plane as well. So that acceleration points into the plane, and we get two vectors, the torque and the angular acceleration, or the change in the angular velocity, are pointing in the same direction. This is going to be a clue that torque is the thing that causes these angular accelerations. Now we can play with this a little bit just as we did. We can change the place where I apply this force, or I can change the amount of force, and that's just going to change the magnitude of the torque and the corresponding magnitude of the change of the angular rate, the angular acceleration. I can change the direction in which I'm applying the force. So if instead I apply the force in this direction, r cross f is going to point out of the screen. That is, or out of the screen or out of the paper vector, the little dot with a hat. And as we do this, let's do it. Force applied that way. Of course, the angular rate is now pointed in that direction, and that angular acceleration is pointed also out of the screen or out of the paper. And if I apply a force in any other direction, we're going to find that it's a lot less effective in starting the acceleration, to the point if I try to apply the force in the same direction, all right, try to push the wheel up, in that case the angle between the position vector and the force vector is 0 degrees, sine of 0 degrees is 0, we get 0 torque and we get 0 acceleration. That's exactly what we saw when we tried to push the wheel and it didn't spin. So this expression for torque, hopefully you've seen, seems to be related, at least in direction, to the angular acceleration, how much the wheel starts to spin up. And we can see that quantitatively by taking an example of just a single point particle, just a little mass here that's shown in the diagram, and seeing what happens if we apply a force, apply a torque, a force from a distance, and how that accelerates. So again, I've got my r term here. It's going to be a little bit of gymnastics here, so it's this way. Our r vector is pointing this way, our force vector is pointing this way, so the torque is pointing out of the screen in this case. If we look at the magnitude of this vector tau, that's just equal to the radius times f, because these are perpendicular to each other. Now remember, the force for Newton's second law is just mass times acceleration. So we can rewrite our torque magnitude as mr times the acceleration. And we can relate this back to our angular quantities by remembering that the physical acceleration, the projected acceleration of an object that's spinning around in a circle, is just the radius times the angular acceleration. So from this we get mr squared times the angular acceleration. And that quantity in front, mr squared, is a measure of the distribution of mass in space. When you think about it, I've moved this mass a certain radius away and started to move it. I would get a very different motion if I moved it closer to our origin point. So the distribution of mass seems to be important for rotation, but that constant is a constant that relates torque to acceleration. So more generally, that constant we call the moment of inertia, and we'll see in another video how we calculate those moments of inertia. But think of it for now as just the distribution of mass in space, and it's going to depend on the masses of your system or object and their distribution through space, and that comes out as a distance squared term. All of those units together combine to form the unit of torque, which is newtons times meters. Now, since torques are so important in determining how an object rotates, we should take a little time to look at the correct practice of calculating the actual torque magnitudes and their directions. So I'm doing an example of just a bar here where I've applied a couple forces, and notice I've been very careful to indicate where those forces are actually acting on our bar. Previously, for our force diagrams, we weren't really that careful necessarily to indicate where the forces were acting. But now, since the torque depends not just on the magnitude of the force, but also where the force acts relative to our coordinate system, the origin of our coordinate system, we have to be very careful to indicate exactly where those forces are acting. So in this case, we've got our two forces. One is pointing up, one is pointing down closer to me, and we're going to use a coordinate system that's located on the far end of the bar, where I have x pointed up and y pointed toward the side, just to make things a little different this time. And so these forces are acting at even steps, one distance L and another a distance 2L, so halfway and all the way on the other side. How do we go about calculating the torques? Well, again, we have to go back and look at our right-hand rule. If we start at our origin at the far side, we're going to point our fingers along the bar and curl our fingers up towards the force vector, and our thumb is indicating the direction of that first torque. So that's going to be a torque that points out of the screen. And then the second one is along the bar and down, and my thumb is pointing back towards into the screen. And so we get these two magnitudes. One is LF into the screen, and one is 2LF, because it's a longer radius, times the force that points out of the screen. And that's a perfectly acceptable way of writing this answer. But let's simplify a little bit, because this out of the screen, into the screen vectors are just the opposite of each other in direction. So I can convert the second one into an out of the screen vector. So that gives me LF minus 2LF, because it's in the opposite direction. And I can add those together to get the net torque is going to act in the minus LF in the out of the board direction, which is really LF into the screen direction. All right, so this thing is going to start rotating around in this direction. All right, so notice I was very careful to use the same origin for the coordinate system for both of these torques. Now what happens if I change the origin of my coordinate systems? Let's say I move the coordinate system somewhere in the middle of our bar. Well, in that case, the first force is going to produce no torque, because there's no position displacement, no vector that goes from the origin to where that force acts. So the first force vector gives 0 torque. The second force vector, though, r cross f, still gives me a torque that goes out of the screen. And in fact, that's the same magnitude, same torque that I got in the last problem. So even though I changed the coordinate system, I still got the same net torque. If you recall about coordinate systems, they shouldn't change the physics of the problem. I should still have the same net torques as long as I'm consistent with my coordinate system. Now the other thing to keep in mind is that because of the cross product, it's only the perpendicular components of the position vector and the force vector that combine to produce torque. So to illustrate this, I've set my coordinate system down below the bar, and I can still compute a torque by drawing a position vector from the origin up to the point where the force acts. And now the direction for that again is r cross f, and that's going to point out of the screen, so that's our out of the screen vector. And the magnitude is just the position vector length times the force times sine of the angle between them, and that's that theta 1 that you see there. Now, we could just go ahead and calculate that geometrically, but we can also see if we can simplify it in terms of some of the quantities that we know. Now notice that theta 1 vector is greater than 90 degrees, and in fact it's equal to 90 plus a little bit that is the same as the little bit between the r vector and the y hat axis. Okay, so that vector down there where the position vector is coming up is just that angle minus 90 degrees. Now it turns out trigonometrically that the cosine of theta minus 90 degrees is equal to sine of theta, so I can replace the sine of theta that's in there with the theta 1 minus 90 degrees, but the cosine of that angle. But that cosine of the angle times our position vector length, the hypotenuse of that triangle, is just the adjacent side, which is just the y component of that vector, and the length of that y component of the vector is just L. So in the end, we get the torque is just F times L, which was exactly the same torque that we got when we measured it with the coordinate system back along the bar. That's because shifting our coordinate system down played no role in changing the moment arm for our force, because that was only based on the horizontal distance. So only the perpendicular components matter, and so sometimes you can very quickly simplify the torque computation by just looking at the problem geometrically as opposed to going through and running the numbers first. Now we can look at torque from another perspective in terms of torque balance. If you recall, we looked at force balance as a way to see how we balance forces acting on a system, in the case where that system is not accelerating. We can do the same by looking at torque balance for things that are not angularly accelerating, not increasing their rotation rate as they are or are not rotating. And it turns out torque balance is a very powerful concept because it provides lots of ways of handling how objects change their orientation and balance. And one of these powerful applications is in the idea of levers. Now, levers is one of one set of our simple machines that include pulleys and inclined planes that we've already looked at. And levers are really powerful because they can be combined in many different ways to add mechanical advantage to all sorts of tasks that we have to do. So here's illustrated 3 different classes of levers, and you can see all kinds of familiar things that we use as levers all the time. Things like hammers and pliers, wheelbarrows, and even weightlifting. Even parts of our body are levers. In fact, we have many levers in our body. Many of the joints that we have at our shoulders, our elbows, even our neck are essentially levers. Now, how do we define these? Well, these are defined as having a fulcrum or pivot, and then at one end of the lever you have a load, and the other lever you have whatever force you're applying to do something with that load. Now, to see how this works, let's just take a simple class 1 lever, which is just a fulcrum in the middle, and then just a bar that's connected to objects. One is the load that we're holding up with our lever, and the other, of course, is the force that we're applying to keep that object up. Now, I've used a coordinate system. Remember, in these problems, we always have to make sure we are very careful about the origin of our coordinate system, so I'm centering my coordinate system at the fulcrum point. And now I can also look at the forces acting on just the bar part of our fulcrum. All right, so these are going to be the forces of interaction. In this case, we've got the interaction with my hand, the force applied onto the bar. Remember, there's an equal and opposite force applied onto the hand, of course. There is the interaction, the contact interaction between the fulcrum point in the middle of the bar, and then there is the interaction between the block and the bar itself. And I've labeled that as the load force. But of course, that's equal to the normal force acting between the block and the bar itself. And if this is a stationary system, of course, that normal force is going to equal the weight as long as it's horizontal. Now, those are the forces acting on the system, and we could add those all up and see that the force is balanced. This system is not accelerating in any direction, and so we can add up these forces and get a relation between them to actually solve for perhaps some unknown force, perhaps maybe the force at the fulcrum. But more importantly, we can also look at what the sum of the torques are. And again, if we don't have any net acceleration to our system, then the sum of the torques are going to equal 0. So we can go through and calculate these torques. So starting from our coordinate system in the middle, we can calculate the torque for the far end of the where the force is applied. So it's R cross F, and that's pointed out of the board. And notice I've not put a direction vector, but I'm just going to choose that to be positive for the case of this problem. The fulcrum contact force is right at the origin, so it's not applying any force at all. And the load force, R from our origin cross F pointing down, is pointing in the opposite direction as our applied force. So we can write that as a negative torque, but keeping in mind implicitly that means it's pointing in the opposite direction as our first torque. We add those together, that's 0. And so that provides us a relationship between the applied force that I'm putting on one end of our lever and the load force on the other end. And that just depends on the lever arms, the distances between the fulcrum and these 2 points on our lever. Now, the way I've written this, those 2 points are balanced, and so those forces would be equal to each other. I'd have to apply essentially the same force as the weight of the block to keep that block in its position as it is. But of course, I can move that around to a different place, and for example, if I move that pivot point closer to where the load is, then the ratio of the load distance to the applied distance, which we call the mechanical advantage, becomes a lot smaller. All right? That load is a much smaller distance away from the fulcrum than the applied distance. So I don't have to apply nearly as much force on my end to keep that block up. This idea of being able to support heavy loads with much less force is one of the great uses for these simple levers. You can end up applying a lot of force on things like bolt cutters or nutcrackers or just lifting heavy things by careful choice of where you apply the fulcrum for your lever. Now, torque balance also gives us a handle on just balance, how things can stay on small footprints on the ground. One of the smallest footprints you can think of is a dancer, a ballet dancer that's on point. As she is balancing on this very small point on the ground, she is balancing not just her body, but she's balancing it through torque balance. So how do we see that happen? Well, in order to have this dancer not rotate down off this on-point position, we have to have a sum of torques that are equal to 0. So how do we calculate the sum of torques? Well, we can start from our pivot point, the point where her toe is actually on the floor, and we can look at all of the different parts of her body, measure the different positions of all her body, because at all of those positions there is a weight force acting. That weight force is, of course, the gravitational interaction of the Earth and the dancer, or at least that part of the dancer. So if we want to add up all of the torques, then what we're doing is adding up all of those position vectors cross the weight vector pointing down. So that's just equal to that. And of course the weight vector is just the little parts of mass that we're going to add up times the gravitational acceleration. Well, that mass term is just a scalar term, so I can slide it over next to the radius term and group those together. And now you see something that perhaps you've seen before, the sum of the masses times the positions where they lie in a system or in an object. Well, that's just the total mass times the center of mass position. So the sum of all the torques is really just the sum of the total mass times the center of mass position cross this gravitational acceleration, because that gravitational acceleration is acting on every single part of the dancer's body. Well, as long as the dancer's center of mass position is directly above the pivot point, in which case it's going to point in the positive x-hat direction, the gravitational force vector is pointing in the negative x-hat direction. Those two vectors are anti-parallel. The sine of the angle between them is going to be 0, so the net torque on the dancer is 0. And as a result, she's not going to rotate down onto the ground. So this just shows us, at least quantitatively, how we can establish balance. And that balance is basically a balance in torque. As long as the center of mass is above the point at which you're in contact with the ground, and as long as gravitational acceleration is also pointing straight down, then those two vectors are parallel or anti-parallel to each other, and so you're going to have the case where you don't have any movement about that pivot point. You're in balance. So to summarize, we've looked at torque. We've derived a definition for torque that is the rotational equivalent of force. By looking at how force causes rotation, we've been able to define this term as the cross product between the distance from the center of rotation to the place where the force is applied. In fact, that r vector, that position vector, can be defined from any origin. And so that cross product is necessary to give the idea of this tangential force acting between the rotation axis and where the thing actually spins. And of course, when you have a cross product, that's just the magnitudes of the vectors times the sine of the angle between them. And then the resulting torque vector points in the perpendicular direction, and that direction is determined by the right-hand rule. The torques are only produced when there is an offset tangential force. That's where that cross product term comes in. You have to have some distance from our center of rotation and the force applying in a tangential direction or some component of it in order to have any kind of torque applied, net torque applied. Now, the torque itself gives rise to angular accelerations. We've seen how that works out quantitatively, and we'll see later on how we can calculate the moment of inertia, which is the conversion factor from torque to angular acceleration. But this is essentially Newton's second law for rotation. Torque is equal to the moment of inertia times the angular acceleration. Now, whenever you're calculating these things, you have to take into account the origin of your coordinate system and use that same origin for all of the torques that have been calculated. We haven't had to worry about this for our force laws because we were just adding those forces vectorially, and where they were relative to the center of mass or origin of the system didn't make much difference. But here that position vector is important in order to calculate where the force is actually acting. So being consistent with our coordinate system is important. Now, applying torque balance, where torques cancel out in any kind of system, gives rise to lots of powerful ways of analyzing pretty interesting simple machines like levers and the balance of systems, including dancers or divers or surfboard surfers. So looking at torque is a great way of looking at how we can see how objects balance each other, and we'll see in the next sort of videos how we can then use torque to see how objects start to rotate or slow down their rotation, how we can use that to convert angular accelerations as objects start to spin up or spin down.